Hi, here's a lecture on frequency modulation, or FM. FM is a type of sinusoidal carrier modulation. All such modulations are based on sending information using either the magnitude or frequency or the phase of a sinusoidal carrier. In the case of FM, we send information by modifying the frequency of the carrier. In particular, here we're considering a scheme in which we have the carrier frequency, f sub c, and we're modifying it by changing it in proportion to the message waveform. So here's a picture of the message waveform. That's the signal, such as audio, which is varying as a function of time. And coming up, we're going to want to consider the bandwidth of this message waveform, that is how much spectrum it occupies as an information signal. And in FM, what we do is we use that magnitude to change the frequency. So here's what FM looks like. Note the magnitude is constant, it doesn't change, but the frequency changes depending on the current value of the waveform, as is indicated in the relationship shown up here. So two key parameters to consider for FM. One is this parameter delta F, which is the frequency deviation. Second one is beta, known as the modulation index, which is the ratio of the frequency deviation to the bandwidth of the information signal W. So beta plays a key role in determining the specific characteristics of the FM modulation. The spectrum of FM is complicated and, as I just said, depends on the modulation index. Fortunately, there's a simple rule for determining the bandwidth, at least. That's known as Carson's rule. And Carson's rule says that the bandwidth is approximately equal to 2 times modulation index plus 1 times the bandwidth of the message signal. So with this in mind, we have two important special cases: Narrowband FM and Wideband FM. So first, Narrowband FM. Narrowband FM is defined by the fact that beta is much less than 2 pi. In this case, Carson's rule indicates the bandwidth should be somewhere between twice and 15 times the bandwidth of the message signal. So you can think of this as bandwidth expansion. The bandwidth of the RF signal is somewhere between twice the bandwidth of the message signal to 15 times the bandwidth of the message signal. For voice, where you only need about 3 kilohertz to send useful information, that means that Narrowband FM has bandwidth somewhere between 6 and 45 kilohertz, depending on the specific value of beta. So a great example of Narrowband FM is NOAA Weather Radio. That's a government radio broadcast of weather information. That's a service that's provided at a bunch of channels around 162 megahertz. That's the VHF spectrum. It's a voice signal, so the message bandwidth is about 3 kilohertz. It's sent with a frequency deviation of 3.25 kilohertz. So beta is around 1, thereby much less than 2 pi. And B, the bandwidth is 12.5 kilohertz. So 12.5 kilohertz for NOAA Weather Radio. This is a very common scheme, especially throughout the VHF and UHF bands. So for example, public safety commonly uses this type of modulation. That's police, fire, and so on. Not exclusively. Many of these services are going to digital modulations. However, many existing police and fire departments still use Narrowband FM. Dispatch services refer to taxi, utility companies, small businesses, and so on. The U.S. government, Federal Communications Commission, defines a service called GMRS. That's General Mobile Radio Service. That's another service around 460 megahertz that operates with Narrowband FM as its primary modulation. And also there's a lot of this kind of modulation around 150 megahertz in the VHF spectrum. The military uses Narrowband FM quite extensively. Government services use Narrowband FM quite often. Also, there's several unlicensed personal uses for narrowband FM. Again, the U.S. Federal Communications Commission defines a service known as Family Radio Service, or FRS, which again operates at around 460 megahertz using narrowband FM. So these are walkie-talkies for private radio communication. All of these have bandwidths around 12.5 kilohertz, typically with a 25 kilohertz spacing. A common variant is narrowband FM with half that bandwidth, 6.25 kilohertz, and that's to improve spectral efficiency. In most of the spectrum, folks are always on the lookout for ways to reduce the bandwidth required. And this is done with some trade-offs. It's not for free, but quite often the spectral efficiency requirements demand systems with narrower bandwidth. So the polar opposite to narrowband FM is wideband FM, generally beta modulation index much greater than 1. We call that WBFM. The classic example here would be broadcast FM, which I think most of you are familiar with. Those are stations at frequencies between 88 and 108 megahertz in the United States. These stations send high fidelity audio. That's requiring about 15 kilohertz to send. Frequency deviation of 75 kilohertz. That gives you a modulation index of 5 and a bandwidth of 180 kilohertz. So here we see it's a relatively wide band signal. That bandwidth of 15 kilohertz in the message signal has been expanded to 180 kilohertz, roughly a factor of 10. We refer to that as bandwidth expansion. So wideband FM has some pros and cons. The big pro is that this makes wideband FM audio quality approximately independent of signal and noise ratio. And this is a rather remarkable property. What this means is that you get pretty high quality audio that's independent of signal noise ratio as long as the signal ratio is above a certain threshold. And I'll come back to that in a moment. AM does not have that property. AM, the audio quality, depends on the signal noise ratio, regardless of what the signal noise ratio is. For FM, what tends to happen is that if you've achieved a certain threshold signal noise ratio, the audio quality is pretty much the same, even as you continue to increase the transmit power. The big con for wideband FM is that it has horrible spectral efficiency. As I just pointed out, we've converted 15 kilohertz of audio to 180 kilohertz of RF. Now, that had the benefit of yielding this SNR independence, but in terms of spectral efficiency, it's pretty awful. So as a result, there's just not too many other applications for wideband FM remaining these days. Some other types of FM. One is radar and one is FSK, or frequency shift keying. Radar comes in a whole bunch of varieties. One of them I think I addressed when I talked about AM modulation. That's pulse radar. There's a type of radar based on FM known as FMCW, or frequency modulated CW, which uses the FM modulation in lieu of pulses. So this is used to allow continuous transmission of a radar signal, which has some advantages in some applications. Frequency shift keying, or FSK, that's simply FM in which the message waveform may only have two possible values. So you end up sending either one frequency or a second frequency. There's no range of frequencies in which you send. So in that sense, it's analogous to continuous wave AM modulation, in which also you send a signal by turning it on or off. In FSK, you send a signal by having it be one of two possible frequencies. FM in the presence of noise and interference, important thing to consider for any modulation. Just like in AM, we have good news and bad news. The good news is that FM is nearly immune to interference. And that's because interference tends to add to the signal, but FM sends information as the frequency, not as a magnitude. So the presence of interference has relatively little effect on FM. The bad news is that the receiver must be able to reliably measure frequency in order to demodulate. And determining frequency is a harder task than estimating the magnitude of a carrier. As a result, this requires a minimum signal-noise ratio, and we end up with a thing called threshold effect. What that means is that it's hard to demodulate FM unless the signal-noise ratio at the receiver is at least 6 to 10 dB or so. So what happens is that above 6 to 10 dB, you have no problem demodulating the signal because you can reliably estimate frequency. But below 6 to 10 dB signal-noise ratio, it becomes hard to reliably measure the frequency and you perform worse. So FM is not the thing you want to use in very, very low signal-noise ratio environments. Furthermore, this effect tends to limit the effective range of FM signals. Now let's wind up this lecture with a few final comments. FM in all its variants, Narrowband FM, Wideband FM, FMCW radar, FSK, and so on, these are very common. And they're not going away anytime soon. Although digital modulations are steadily eroding the number of places where FM is used, but there's just a few places where FM will likely remain into the indefinite future. Narrowband FM, in particular, is favored over AM, and that includes double sideband and single sideband, for applications in which audio quality and interference immunity are more important than the things that AM is good at, which is bandwidth and range. So in other words, if bandwidth and range are the primary considerations, then that tends to lead you in the direction of amplitude modulation. If, on the other hand, the quality of the audio, which is improved by this bandwidth spreading effect, and interference immunity are the more important things, then you'd probably tend towards narrowband FM. So this explains why narrowband FM tends to be preferred in things like public safety communications, police and fire and so on. Those are applications where the range does not have to be continental, for example, and audio quality is very important. So narrowband FM in particular has an important role and an important advantage over AM in some applications. That concludes this lecture on frequency modulation.